Hi. Good afternoon, everyone. Today I will be presenting GSNet, Joint Vehicle Pose and Shape Reconstruction with Geometrical and Scene-Aware Supervision. So the aim of this paper is that given the input image from the view of self-driving car to reconstruct 3D car meshes onto the original image, as you can see in the second image, and then also a novel aerial view of reconstructed 3D traffic scenes, as you can see in the third image. Okay, let's get started. Okay, so one of the challenge in traffic scene understanding is like to perceive the 3D attributes such as like translation, rotation, and shape of the vehicles. And this one is very hard to get from RGB image. So models usually they combine the LiDAR or other stereo cameras to get this kind of information. Also in traffic scene understanding, representing 6 degrees of freedom object pose and detailed 3D shapes is very informative for like 3D shapes and reconstructions. And also there is like several methods doing this with only RGB images, and they can be categorized into two categories, like fitting based and regression based. Fitting based usually consists of two stages. In the first stage, they extract 2D image cues from bounding box and key points, and then fit that into 3D template vehicles that best matches the 2D image observations. And then after that, they do post-processing steps that's usually very time-consuming due to iterative nonlinear optimizations. And these methods are not applicable for real-time autonomous driving because it takes a lot of time. And then second methods are regression-based, which directly predicts 3D pose and shape parameters with a single efficient forward pass from deep networks. And this GSNet is a regression-based method. So it's a little bit introduction about the method. It's end-to-end multitask novel network for jointly estimating 6 degrees of freedom car poses and reconstruct dense 3D shapes from single RGB image in urban street view. Also, it utilizes a unique 4-way feature extractions and fusion schemes. I'll talk about all of this later. This 4-way feature extraction consists of ROI features, global features, and multi-scale features. And also it's designed to explore more potential feature source and use an effective fusion scheme to supplement ROI features. One of the idea behind this is that like current models that do 3D shape and pose reconstructions, they mainly focus on ROI features. And this method also try to focus on the global features, which is like cars nearby and other geometrical informations. Also, GSNet uses divide and conquer 3D shape representations. This is also very important contribution of them, and I will talk in depth about this later. And the last part of this model is multi-objective loss functions. This loss function considers the geometric consistency using projection of the key points, and then additionally it incorporates a scene-aware term considering both inter-instance and instance environment constraints. So this loss also like take into consideration the environment of the car, since in the self-driving environment the car in the nearby is the car nearby is very important to make decisions. Okay, so the pose and shape representations. So the 6 degrees of freedom pose for each instance consists of translation vector, which is represented by the center of the object coordinates, x, y, z, and also rotation vertex, which consists of roll, pitch, and yaw, with respect to coordinates of the camera given in the system. Also, the divide and conquer shape representation, which is introduced in this paper, is is used to represent the vehicle shape with dense mesh consisting of 1,352 vertex and 2,700 faces, which is, and this is made from the CAD meshes provided by the Apollo car dataset. So in the Apollo car dataset, there is like 79 available CAD models, and then they use K-means algorithm to cluster them into 4 clusters with a similar shapes. Like some of the cars different model, but they are very similar to each other. And also they learn low dimensional basis for each cluster, for each of these 4 clusters using PCA, and predict principal component coefficients for each cluster. And then final shape is, and then they use that 4 meshes and blend them together using classification score. And using this method, this divide and conquer method, they achieve much better results than like using PCA on each mesh separately, which is like 79 of them here. So here is the image of the divide and conquer 3D shape reconstruction models. So first they get feature shape, fused shape features, and then they divide them into 4 clusters. And then they also do classifications, which CAD is in which category. And then at the end, they blend all of them together and get only one mesh. And also, yeah, they say that this strategy achieves lower shape reconstruction errors compared to other methods. And you will talk about them in evaluation study. Here's the network architecture. And I'll talk about each section separately. So first thing they do is that they extract 4 types of features from traffic scene and then fuse them together and then use the multitask prediction, which are done in parallel to estimate 3D translation, rotation, and shape. So here, as you can see, first they have the input, and then they got like the 4-way presentations, which is ROI features, detected boxes, 2D key points, and heat maps of the key points. And then they go through some intermediate networks, and then they will be fused to get some specific outputs, like the ROI features, detecting box and key points will be used to get the translation, and then features and key points and heat map will be used for rotations. And for 3D shape reconstruction, they will use ROI features and heat map, key point heat maps. Yeah, sorry, feature extraction and representation. Yeah, so based on the bounding box ROI pooling, they extract appearance features for each instance, and they use FPN as a backbone. And in parallel, they also detect instance and fed to fully convolutional subnetworks to obtain 2D key point heat maps and coordinates. And then the key point heat map, they use these key point heat maps to help the network discriminate the occluded instance. So this slide is about getting this 4-way representation. How do they produce it? Like, as you see, there's a backbone, and then through ROI pooling, they get ROI features. And then for each detected instance, they get 2D key points from heat map regression. And also they have detected boxes. And then after that, detected boxes are represented as a 2D box centers with BX and BY, the coordinate of the centers, and BV and BH as the width and height respectively in the pixel space. And then they have the camera intrinsics, which is this vector consists of the focal length in pixel unit and the principal point of the image center. And then using this, they transform the coordinate of the detecting boxes to corresponding coordinate in the world frame, 3D frame. And also, yeah, each key point is represented as a 3 value vector. And here, and the first 2 X and Y are the coordinates of the image, and the second one is the visibility. As we know, every car is self-occluded, so there is some key points that's always occluded behind. Also in the Vision scheme, they convert they convert the extracted four-way inputs into 1D representation separately and decide which feature to use for compiling each task by prior knowledge. So now we are talking about the second step. So each of the extracted features will be transformed to one-dimensional vectors, and then they will be used for predictions. And then, also for like global key point positions and detected boxes, they apply two fully connected layers to convert them into higher level features. And for ROI feature maps and heat maps, they adopt sequential convolution operation to reduce their spatial size. And after that, for predicting the translation vector, which is mainly affected the object's location and scale, they concatenate the ROI features and 2D key point features and box position features for regretting the translation. And then for rotation, they use ROI features, heat maps, and the key point features as an input. And for estimating the shape parameters, they aggregate the ROI and the heat map features. Also, for the prediction, they have 3 parallel estimation branch, and also each branch directly regress the targets. So as you can see, first each features will go through some networks, and then they concatenate them and then predict the translation, rotation, and shape reconstruction from some of them, which are very important to output of this. Okay. And then another thing they contribute is the loss, or they did a little bit. They just want the model to learn not only from ROI features or the annotated features, but also they want to give extra informations from the environment of the other other vehicles in the image. So like for 3D semantic key points, the predicted mesh, on the predicted mesh, they reprojected each key point through these equations, where here the K is a camera intrinsic matrix, and then U0 and V0 is a projection point in the pixel units. So after doing this reprojection, they calculate the loss for each key point using this equation, and using L2 loss, and then they calculate the total loss for each key point by this equation. In here, the Vi is the visibility of the key point. It's Boolean. As I said, each key point, every car is self-occluded. So no matter from which angle you look, there are some key points which are occluded by some part of the car itself. And this visibility indicates that one. And also they have scene aware loss. Also, from the observation of the data set, like most of the car have the common ground. So they make they make a plane using 3 meshes, and then they calculate the loss of the other car if they are on that plane or not. And then this is called inter-instance coplanar loss, and is calculated in this way. And also, in addition, if we take a look in each vehicle alone, each vehicle also has like 4 wheels, and also they should be in the same plane. So we can also make intra-instance loss, which will help us to better visualize the 3D shapes. And also the equation of the intra-instance loss is similar to this equation. In this case, the 3 point is chosen within the predicted mesh of each vehicle, and then the rest. So here is a kind of image of each losses. So they have like separately translation, rotation, and mesh laws. And then they also added like scene aware laws and geometric consistency laws. Yeah, so for the regression loss for mesh and rotation is calculated in this way. And then for translation vectors, they used L1 loss, and they say that it works better than L2 loss, and they did experiment in the ablation study. And then for rotation vector, they used the following laws. And also they have classification laws, which classify which car goes into which cluster. And then the final loss will be summation of the all loss with some coefficients before them. And in the experiment, they used Apollo car 3D dataset for training. And then they also used Pascal 3D plus dataset, but only the car instance from them. And they used Kitty dataset only for evaluation. And in the Apollo car 3D dataset, they have like new evaluation metrics, which is R3DP, which has like 10 threshold for jointly measuring, and that they measure the translation, rotation, and car shape at the same time. And then for translation loss, they use Euclidean distance, and for rotation, they have Arcos distance, and for 3D shape reconstruction and parallel mesh, a predicted mesh is rendered into 100 view and compute IOU with ground truth masks, and the mean IOU is used. Yeah, okay. So here's the ablation study of the GSNet. So as I said, they have like four-way feature fusions. So they did ablation study in using only some of them. So like using only ROI features, and here like the result for 3D shape reconstruction and 6 degree of freedom error. And as you can see, when they use all of the features, they get the best result. And also, we talked about the losses that they introduced. So here, as you can see, when they use all of the loss together, they get a much better result compared to the just loss of the 3D shapes, or just adding, when they add more loss, the result will be much better. Okay, here is the performance of the GSNet on the Apollo Car 3D datasets. Hard to see. Okay. So the result of the GSNet on on Apollo Car 3D dataset is state of the art, except one section. But in the mean result, it achieves better result than 3D RCNN, and also the time inference. The time inference is a little bit worse than others, but the output result is much better, especially in when we calculate the mean of R3DP. And also, as we said about divide and conquer, they divide all of the CAD models into four categories and then blend them together to get one mesh. And then here, when you don't divide into four categories and use PCA on each of the meshes or CAD model separately, and when you do divide and conquer, and then the result will be like here, as you can see, the single PCA and then divide and conquer model, and the result is much higher. The error is lower, and then MAP is higher. And also they did they calculate the angular error on Pascal 3D data set, and the GSNet achieved like much higher accuracy and lower angular error. So here are some qualitative results of okay, the first row is basically third row is so this is the second row is a result of the direct based approach, which is from another paper, and the third row is a result of the GSNet, and the last one is 3D shape reconstructions. And as you can see here, there is some like extra stuff or some misdetection in the second row, but the third row has much better results. And also this is the result of the GSNet on the Kitty dataset, which it has not been trained on, but they just evaluated in the Kitty dataset, and they get this kind of results. That will be all from me.